Good morning. I'm so pleased to welcome students, faculty, staff, our Board of Trustee Chair, Chris Whitman. Great to have you here, Chris. Trustee Judy Von Bucher's here. Thank you, Judy. Members of the media, honored guests, and of course, the whole RIT community. I'm President Bill Destler, and I thank you for joining us here for an announcement that I promise will be well worth your time. This is a historic day for science. As you may have heard this morning, the International Laser Interferometer Gravitational Wave Observatory, or LIGO, announced for the first time that it had detected actual gravitational waves, confirming theories put forth a century ago by Albert Einstein. Amazing, isn't it? Almost exactly 100 years. So, this is an incredible, science-altering news that opens up a myriad of possibilities for what we can learn about the universe. But what's also amazing, and what makes me burst with pride today, is that RIT and a group of researchers here have played a very important role in this discovery. RIT is incredibly proud of Dr. Manuela Campanella and her team at the Center for Computational Relativity and Gravitation at RIT, which is part of our College of Science. Their work and their dedication to their field exemplify the kind of internationally recognized research that increasingly is happening here at RIT. So let me bring up Dr. Campanelli, director of the center, who will introduce you to her team and give you the details of their role in this amazing discovery. Manuela.
Thank you, President Destler, for this wonderful introduction and kind words. This is a day of days. This is a day where every scientist should walk very proud of. We are very proud to be part of the Einstein legacy. We as CCRG want also to thank President Destler, Provost Hafner, Vice President Ryan Raffaelli, RIT leadership team, and its Board of Trustees, as well as College of Science Dean Sofia Magalakis, and our department head of the School of Mathematical Science, Mihai Barbosu, for bringing us at RIT and for the support they have given to us for the center today to be successful in its research endeavor. We are very proud to be part of the LIGO scientific collaboration that announced this important discovery this morning. This announcement has a great significance for RIT. It has a great scientific significance for the entire world. It is the first confirmation, direct confirmation of the existence of gravitational waves that Einstein predicted 100 years ago. It is the first confirmation of the existence of black holes, as well as the observation of binary black hole collisions that the RIT team contributed to. In other words, this is an historical moment in science. This is the discovery that will mark the opening of a new era for astronomy called gravitational wave astronomy. A new window into the universe is being opened today. Among the authors of this amazing discovery paper are 6 researchers in my team. The paper has just appeared in Physical Review Letters today after the announcement at the National Science Foundation you heard this morning. I would like to introduce the team members and as well as the teams of the entire CCRG now. When I do so, please, I'll call your name, raise, and face the audience so you can be recognized. Dr. John Whelan, Associate Professor in the College of Science, principal investigator of the LIGO scientific collaboration at Rochester Institute of Technology. Carlo Lostow, professor in the College of Science and founding member of the CCRG, a key author of the 2005 breakthrough in numerical relativity that played a role in the today's discovery. Richard O'Shaughnessy, assistant professor in the College of Science, a member of the LIGO scientific collaboration, who will talk more on the importance of this discovery. And then James Healy, a postdoctoral researcher working at the center who works with Dr. Lustow. Jacob Lange, a College of Science PhD student in astrophysical science and technology who is working with Dr. O'Shaughnessy. Ye-Wan Hao Zhang, a PhD student who worked with Dr. Whelan. And now the rest of the team. Dr. Hans-Peter Bischoff, Professor of Computer Science, Thomas Golisano College of Computing and Information Science, and a founding member of CCRG, and one of the key members who produced the visuals that you are going to see today. Dr. Josef Zlochower, Associate Professor in the College of Science, and also a key author of the 2005 breakthrough in numerical relativity. Dr. Joshua Faber, Associate Professor in the College of Science, who works in modeling neutron star coalescence, which is one of the sources that LIGO will detect in the future. Dr. Jason Nordhaus, Assistant Professor in Mathematics and Science at the National Technical Institute of DAF, who is working on core collapse supernova, also an important source for the LIGO detector. Then PhD student Dennis Bowen, College of Science PhD students in astrophysical science and technology who work closely with me on binary black holes. Jackson Henry, undergraduate student in physics in the College of Science who work with Dr. Whelan to study the detection of geometry of LIGO. Brennan Ireland, a College of Science PhD student who work also with me on binary black hole coalescence. Monica Rizzo, undergraduate student physics in the College of Science who work with Dr. O'Shaughnessy. Jam Sadiq, a PhD student in the College of Science, a graduate Fulbright student working with Josef Zlochower, also on binary black hole coalescence. And Zach Siebelman, PhD student who worked with Joshua Faber on binary neutron star coalescence. Please join me in giving this incredible team a round of applause. And the video. And now I would like to show you a brief video that will tell you a little bit more about our work.
In November of 1915, Albert Einstein presented his field equations of general relativity to the Prussian Academy of Science. This was a revolutionary idea in physics at the time that fundamentally changed our understanding of how the universe works. The idea that space and time are dynamical quantities that are influenced by the presence of matter was completely mind-blowing and unique. It changed our understanding of gravity itself.
Gravitational waves is among the most amazing prediction of the theory of Einstein's general relativity. Gravitational waves are disturbances of the space-time produced by the collisions of astrophysical objects like binary black holes and neutron stars.
General relativity is important for neutron star calculations. They're relativistic objects. Newtonian calculations don't capture the full physics of what's going on. Many of the elements we see in the universe were created by neutron star mergers, and it takes a sophisticated level of nuclear physics in order to make accurate predictions and really be able to test models.
For a vacuum simulation, we typically use up to around 1,000 computers for a single simulation. If you start to add matter on top of that, then things get even more complicated, and rather than using 1,000, you'd be using tens to possibly even hundreds of thousands.
The group here is one of the world leader groups in the field of numerical relativity. 10 years ago, we solved for the first time the equation of general relativity that describes how two black holes collide and merge in strong field gravity.
It was called a breakthrough in numerical relativity. Finally, we obtained a way of solving this problem.
Some of the revolutionary work that was done was to perform some of the first simulations of binary black holes. These simulations, for the first time, allowed us to predict what we actually expected.
Nobody has really, until recently, seen a gravitational wave. So the lab generates templates, an idea how a gravitational wave could look like, so the scientists at LIGO have a much easier time to actually find them.
We made predictions about what the gravitational waves from binary black holes look like, detailed and accurate predictions.
Einstein predicted gravitational waves as a part of general relativity, and he said they were most likely real and that we would most likely never see them because they were too small. And he is partly right and partly wrong.
Several members of the CCRG are members of the LIGO Scientific Collaboration, or LSC. The LSC is a 1,000-member collaboration, all collaborating to analyze the information from this interferometric gravitational wave detector.
LIGO, the Laser Interferometer Gravitational Wave Observatory, and it's this kilometer scale interferometer. So they look for changes in the geometry of space and time that would be caused by gravitational waves by looking at changes in distances, and it can make very, very fine measurements in not an absolute distance, but in the difference between two lengths. So it can tell if one of its arms is very slightly longer than the other. And it turns out that in order to see the kind of gravitational waves we expect there to be around, you need to make these distance measurements incredibly finely, to a thousandth the size of a proton.
Late last year, advanced LIGO turned on and immediately detected gravitational waves of precisely the form that was predicted here at RIT by detailed simulations of Einstein's theory of relativity.
The LIGO announcement is both a very historical and emotional moment in science, especially when our research contributed to the identification of the first gravitational wave from a binary black hole merger.
I believe that what LIGO have detected is perhaps the most important result in the last 50 years in physics. This opens up a new area in science, in astronomy, which is gravitational wave astronomy.
We've now kicked off the era of gravitational wave astronomy. And so, this is an important milestone to make the first direct detection of gravitational waves, but it's the beginning of the story, not the end of the story.
Now we have a completely new window into the universe that will teach us many things that we had no access to before.
And now here, I would like to introduce my colleague, Dr. John Whelan, who is the principal investigator of the LIGO Scientific Collaboration, to tell us a little bit more about this amazing discovery.
I should say I'm the principal investigator of RIT's group in the LSC. I'm not in charge of the whole LSC. When I first came to RIT in 2008, the CCRG already had a world-renowned numerical relativity group and was looking to build a group carrying out gravitational wave observations in the LIGO Scientific Collaboration. The LSC is an international collaboration of over 1,000 scientists at nearly 100 institutions on 5 continents. LSC members improve the LIGO detectors, analyze the data for gravitational wave signals, and interpret the results. When I arrived, I was leading the internal review of all the searches for compact binaries and about to begin reviewing the first search for binary black hole in spiral, merger, and ring down with initial LIGO. Since then, our group has grown, and among the contributions we've made to the LSE is playing a major role in interpreting the first confirmed binary black hole signal. Today, the LSE and the Virgo collaboration have announced the detection of this signal, received at the 2 LIGO detectors in Louisiana and Washington State at the start of Advanced LIGO's first observing run last September. The primary paper has been published in Physical Review Letters, volume 116, if anyone's taking notes. And there are 12 other papers that are being released today, which have been submitted to various journals, explaining the results of this discovery and its significance in further detail. Gravitational wave scientists perform sophisticated match filtering of our data using accurate templates. This is to confirm the significance of our detections and to rule out false alarms. Fortunately, this signal, as recorded in LIGO, is actually so strong that we can just show you the data and point to the signal. There it is. And it looks just like the numerical simulations. To explain more about the analysis and RIT's involvement, I'd like to introduce Dr. Richard O'Shaughnessy, the other faculty member whose main research is on gravitational wave data analysis, and then also Carlos Lusto, who has been working directly with the analysts to provide insights in the CCRG, from the CCRG simulations.
Well, I'm happy to say Einstein was right. As John said, what we're showing here is what we saw when we woke up on the morning of September 14th and checked our email. And we were told, wow, look at this. Because what we're showing is what LIGO sees, our response. Now, it's more sensitive to some frequencies than others, just like your ear. So this only shows up when it becomes a particularly high frequency signal right before merger. But you see a couple of wiggles leaping out at you from the data. And this is the data. Below, from both instruments, and it looks exactly the same. So clearly we've seen something. Even more fascinating, and if you look closely, you will see that we have error bars. We can reconstruct the signal and compare it with the detailed predictions of Einstein's theory of gravity as produced by detailed supercomputer simulations. And they agree fantastically well. Most of you in the back probably can't even see the error bars because the signal is right on top of them. As I said, Einstein was right. So what LIGO is reporting today is therefore 3, in my mind, fantastic discoveries. First, obviously, the direct detection of gravitational waves. Second, the observation of coalescing binary black holes that agrees precisely with Einstein's theory of general relativity, allowing us to perform high-precision tests of fundamental physics that had previously been completely inaccessible to us for the first time. And third, we discovered binary black holes, something which, because they're black, had been completely inaccessible to us. These objects we had expected to exist at the end of the lives and deaths of massive stars. One of my colleagues, Dr. Jason Northouse, can tell you more about that. But never before, although we had expected them to exist, had we seen them at that mass, ever, or let alone 2 of them, together, so close together. And remember, in order for this to happen, they have to be well inside the size of the stars that formed them, spiraling together and coalescing. This tells us new things about the lives and deaths of massive stars. We now know, because we saw this at almost the instant that Advanced LIGO turns on, that these occur frequently throughout the universe. So frequently, in fact, that if you account for all of them that occur out to the beginning of the universe, that we expect at least one gravitational wave is passing through you from things like this every about 15 minutes. So this discovery shows directly, because we can reconstruct the properties of the source by comparing with these detailed simulations. And that is one of the essences of our contribution at RIT. We directly compare, we directly do these comparisons between the data and the results of these simulations. These comparisons allow us to measure specifically what we just saw, what was responsible for this wave, why we know it was a pair of black holes. This means that now we've transformed gravitational waves not just into a detection of a new realm of physics, but we've made it into an engine of astronomical discovery. Now, of course, this is only possible and enabled entirely by our ability to correctly understand the predictions of Einstein's theory of gravity. This is the interaction of two black holes. And the data analysis project that I described, which is central to our work in the LSE, involves the direct comparison between gravitational wave data and the predictions of Einstein's theory of gravity as performed on supercomputers, which Dr. Lusto will describe momentarily.
So what I'm going to speak about is how we generated these waveforms from theoretical studies, essentially solving general relativity equations. And I will show this in an animation, a computer animation that we have prepared for explaining how we do that. So those are the waveforms generated by these two black holes here orbiting around each other. You see the fabric of the space-time that is represented by the grid of our simulations. The black holes are spinning, that's represented with the arrows. The orbital plane process as the black holes get together. We have the waveform in the bottom, and that's what is going to reach us on Earth. The final explosion releases an enormous amount of radiation and outshines the whole universe by a factor 50 or so. The release is equivalent to, in the last 0.2 seconds, convert twice the mass of the sun, annihilate it, and convert it into gravitational waves and send it all around the universe. So as was mentioned before, the significance of this discovery announced today is two leaps forwards in our understanding of nature. One, the existence of gravitational waves that Einstein predicted 100 years ago and describes the fast motion of these two bodies, motions comparable to the speed of light, and then the strong field limit of general relativity, in fact, so strong that light cannot escape from them. I'm speaking about black holes. We have a direct detection of black holes, and we have been able to produce these simulations only since 10 years ago. It was a 40 years standing problem. Nobody could solve. Only 10 years ago, we have been able to solve this into supercomputers. Let me tell that this simulation that we have seen here briefly for 30 seconds took 6 months running in our supercomputer here in RIT. And it took only 6 seconds in nature to produce, okay? That tells you how difficult are these problems to solve. And we are proud to be part of the family of RIT and contribute to the huge step forward that science has taken today. Thank you very much.
very special day, I think, for science in general, but also for RIT. And let me emphasize a couple of things that really our speakers are a little bit modest about their own contributions. I won't be modest because I'm so proud of them. First of all, this work on binary black holes, postulating their existence and then predicting the kinds of gravitational waves that would come out of them is the product of more than 10 years of work, starting with a seminal paper co-authored by Manuela Campanella and her colleagues, in which they discovered a very elegant way of solving Einstein's equations that permitted this kind of simulation to occur. That is really the foundational element that allowed these predictions to occur. And remember, these predictions have predated this present discovery by years. So in fact, the LIGO experiment, as wonderful as it is, and it's a tremendous technological achievement, is actually a confirmation of the prediction of the work of these individuals that you see here. It's really something special. Yeah. You know, and finally, I'd say that you know, RIT, of course, is a place where research is an increasingly important part of what we do, and we're proud of the work done by our researchers. But I think you also saw that we have both undergraduate and graduate students working on these problems. There aren't very many people who would involve undergraduate students in this kind of project. I think we should be very, very proud of that. I think that probably the best way to handle questions would be to have perhaps our speakers be available for questions from the media. We have quite a few media representatives here. But this is a proud day for RIT, a proud day for science, clearly a proud day for the LIGO team. I don't want to understate the elegance of the experiment which they conducted in order to make these detections. But remember, it kind of started with these guys right here. Thanks very much. What makes me burst with pride today is that RIT and a group of researchers here have played a very important role in this discovery. RIT is incredibly proud of Dr. Manuela Campanella and her team at the Center for Computational Relativity and Gravitation at RIT, which is part of our College of Science. Their work and their dedication to their field exemplify the kind of internationally recognized research that increasingly is happening here at RIT. So let me bring up Dr. Campanelli, director of the center, who will introduce you to her team and give you the details of their role in this amazing discovery. Manuela.
Thank you, President Dassler, for this wonderful introduction and kind words. This is a day of days. This is a day where every scientist should walk very proud of.
As you may have heard this morning, the International Laser Interferometer Gravitational Wave Observatory, or LIGO, announced for the first time that it had detected actual gravitational waves, confirming theories put forth a century ago by Albert Einstein. Amazing, isn't it? Almost exactly 100 years. So, this is an incredible, science-altering news that opens up a myriad of possibilities for what we can learn about the universe. But what's also amazing, and what... Good morning. I'm so pleased to welcome students, faculty, staff, our Board of Trustee Chair, Chris Whitman. Great to have you here, Chris. Trustee Judy Von Bucher's here. Thank you, Judy. Members of the media, honored guests, and of course, the whole RIT community. I'm President Bill Destler, and I thank you for joining us here for an announcement that I promise will be well worth your time. This is a historic day for science.
We are very proud to be part of the Einstein legacy. We as CCRG want also to thank President Dassler, Provost Hafner, Vice President Ryan Raffaelli, RIT leadership team, and its Board of Trustees, as well as College of Science Dean Sofia Magelakis, and our department head of the School of